Hey there, welcome back. You're here because you want to get to grips with the really interesting stuff and you want to do it quickly. You love those moments when a complex idea suddenly makes sense and you want to avoid wading through all that jargon, which is exactly what we're all about. So today, we're going deep on something that might sound a little bit like science fiction. We're talking about the possibility of harnessing the Earth's rotational energy.
Yeah, it's a pretty wild idea. We've got a detailed essay and some summaries of a recent experiment that are just fascinating. So think of us as doing the digging for you, extracting those really interesting nuggets of information about a potential game changer for renewable energy.
I like that a lot. So our goal today is pretty straightforward. We're going to explore this concept of generating electricity from the spin of the Earth and its magnetic field. We'll be looking at the science behind it, the experiment that's got everybody talking, and what it could all mean in the future.
And we're going to try and have some fun along the way.
Always a good plan. So let's set the scene a little bit. The world's demand for energy, it just keeps growing and growing, right?
It certainly does.
And while we're seeing huge advancements in solar and wind power, the search is always on for that next big breakthrough in renewables.
Right.
But when you think about it, the Earth itself is this massive, constantly spinning ball of kinetic energy. I mean, it's an incredible amount of energy just sitting there.
A colossal reservoir.
Exactly. But for years, the thinking was that we just couldn't tap into that energy directly for electricity. It was considered to be impossible, theoretically, because of how it interacts with the Earth's magnetic field.
That's right. The assumption was that any attempt to capture that energy and convert it to electricity would be canceled out almost immediately.
Like a dead end, right.
Yeah, by the fundamental laws of electromagnetism within the Earth's magnetic field.
And here's where it gets really interesting. A recent experiment has actually challenged this fundamental belief.
And it's not just challenged the theory, it's actually demonstrated a working device.
Okay, so now I'm really intrigued. Let's get into the science behind all of this. Our planet spins at a speed of about 1,670 kilometers an hour at the equator. I mean, that's just mind-boggling when you think about it. And then we have the Earth's geomagnetic field, that invisible shield that protects us from harmful solar radiation. It's generated by the movement of molten iron deep inside the Earth.
The dynamo effect.
That's it. And it's also responsible for the northern and southern lights, which is just beautiful.
Yeah, absolutely. So the traditional understanding of Faraday's law, which is a cornerstone of how we understand electromagnetic induction, the thinking was that if you tried to generate a voltage within the Earth's magnetic field using a normal conductor, the electrons in that conductor would rearrange themselves.
And they would essentially cancel out any usable voltage.
Right.
Exactly. It's like trying to push water uphill. It's just not going to happen.
So it's like the laws of physics were saying, nope, not going to happen.
Right. And for nearly 2 centuries, this has been seen as this insurmountable barrier to accessing this massive source of energy.
A real roadblock.
But then the work of Christopher Chiba and his team came along. And it seems like they've actually found a way around this barrier.
They might have done. They've developed a working prototype. And while it's small, it does work, which is pretty amazing.
So what did they do that was so different? I mean, what's the secret sauce here?
Well, at the core of their experiment was this hollow cylindrical shell. And it was made from a special material called manganese-zinc ferrite.
Manganese-zinc ferrite. Oh, okay. So now we're getting into the technical stuff. But why was this material chosen? I mean, was it just random?
Not at all. It has some very specific properties that make it perfect for this job.
Okay, so let's break it down. Why manganese-zinc ferrite?
Well, for one, it's got very low electrical conductivity.
And that's important because...
Because it helps to minimize that electron rearrangement that we were talking about.
Ah, okay. So the electrons don't cancel out the voltage as easily.
It's like trying to conduct electricity through wood versus through metal.
We want the least flow possible to prevent that self-canceling effect.
Precisely. And then there's another important property. It's called magnetic permeability.
Okay, so magnetic permeability, what does that mean?
It basically means that it allows the Earth's magnetic field to pass through it without changing very much. You could almost say it's transparent to the magnetic field.
And that's crucial for this whole thing to work, right?
Absolutely. So they've got this special hollow cylinder about 30 centimeters long. It's not huge.
No, but big enough to experiment with.
Right.
And the fact that it's hollow as opposed to being solid, that's a key part of the design.
Definitely. Now think about the positioning of this thing. It wasn't just sitting on a table in the lab.
So how do they orient it?
Well, it was very precise. They placed it at an angle of 57 degrees relative to the ground.
57 degrees. Why that specific angle?
Well, that angle is perpendicular to both the Earth's rotational velocity vector and the magnetic field lines.
Okay, so it's positioned to maximize the interaction with both of those forces.
Exactly. And then to measure whether any energy was being generated, they placed electrodes at each end of the cylinder.
Clever. And so then they started testing.
Right. They ran tests both in the lab and out in the field. They rotated the cylinder to different angles relative to the magnetic field and carefully measured the voltage.
So meticulous.
Right.
And they even ran some control experiments, just to be sure.
Yeah. They used solid ferrite cylinders and cylinders made from other materials just to make sure that what they were seeing was actually because of the specific material and the design of their hollow cylinder.
And what were the results? I mean, did it work?
Well, this is where it gets really exciting. The experiment consistently produced a small direct current voltage. It was only about 17 to 18 microvolts.
Microvolts. I mean, that's tiny, right? You're not going to power your house with that.
No, not even close. But the fact that they detected anything at all, that's the breakthrough.
So it's a proof of concept.
Exactly. And what's even more interesting is that when they changed the orientation of the cylinder, the polarity of the voltage flipped.
And when they positioned it at a 90-degree angle to the magnetic field, the voltage completely disappeared.
Right, which is exactly what their theoretical models predicted.
So it wasn't just some random fluke. They were really onto something significant here.
It seems that way.
Yeah.
And the fact that they could replicate these results in different locations and under different conditions, that just adds to the credibility of their findings.
Absolutely. And the control experiment that they did with the solid ferrite cylinders.
Right. Those cylinders didn't produce any measurable voltage at all.
Which basically confirms that the hollow design and the specific material they used, those are the key factors here.
It really does seem that way.
This feels like a really big deal. It's like after centuries of scientists believing this was impossible, somebody has finally shown us a way, even if it's just on a very small scale for now.
I think you're right. And this opens up this whole new area of research in both physics and energy. And it hints at the possibility of maybe one day tapping into these planetary scale energy sources.
Okay, so let's think big picture for a minute. If this technology could be scaled up, what are the potential applications?
Well, the ultimate goal would be to have a clean and practically unlimited source of energy. Imagine a future where we're not so reliant on fossil fuels.
That would be incredible.
Yeah.
But how do we go from this tiny prototype to something that can actually power our homes and cities?
That's the big question, isn't it? Scaling up this technology is going to require a lot of innovation.
What kind of innovation are we talking about?
Well, for one thing, we need to find new and improved materials with even better electromagnetic properties.
So materials that can interact with the Earth's rotation and magnetic field more efficiently.
Exactly. And we need to find ways to optimize the design of these devices. The cylinder might not be the best shape in the long run. And then there's the idea of using a modular approach.
So having multiple units working together.
Right, to generate a substantial amount of power.
Now, there's another side to this that we need to talk about. When we're talking about tapping into something as fundamental as the Earth's rotation, we have to consider the potential downsides.
Yeah, you're right. Extracting energy from a system that large, could it have unintended consequences?
I mean, could we slow the Earth's rotation down or something?
Well, theoretically, any extraction of energy from the Earth's rotation would cause it to slow down a tiny bit.
But with the current experiment, that effect is going to be negligible, right?
Absolutely. But if we're talking about large-scale energy extraction over a very long period of time, it could potentially affect things like tidal patterns and even the length of our day.
Wow. So that's something to think about. It's not just about getting clean energy. It's about doing it in a way that doesn't harm the planet.
It's a balance for sure. But beyond the energy applications, there are other potential benefits to this kind of research.
Like what?
Well, it's giving us a much deeper understanding of the complex relationship between the Earth's rotation and its magnetic field. And this knowledge could lead to advancements in other fields, like geophysics.
So it could have a ripple effect across multiple scientific disciplines.
Exactly. It could inspire new technologies in areas like electronics and sustainable engineering. This is about more than just energy. It's about expanding our fundamental scientific understanding.
So where do we go from here? What are the next steps in this research? What are the big challenges that need to be overcome?
Well, the biggest hurdle right now is the huge difference between the tiny amount of power that the current device produces and the amount of power that we need to make this practical.
We're talking about a massive increase in power output.
Orders of magnitude.
Like going from a single LED light to powering an entire city.
A good analogy. And achieving that is going to require some major breakthroughs in material science.
So we need to find materials that are way more efficient at interacting with the Earth's rotation and magnetic field.
Precisely. We also need to explore different designs. Maybe the cylinder isn't the most effective shape. And then there's the whole challenge of scaling up.
Going from a 30-centimeter cylinder to something that can power homes or even industries.
That's going to be a huge engineering feat.
And we need to make sure we do it in a way that doesn't negatively impact the environment.
Right, so we're going to need sophisticated computer models to test different scaling strategies. We need to understand the potential impacts of these large systems, and we need to do some serious theoretical studies to really grasp the long-term consequences for the Earth.
This sounds like it's going to require a massive collaborative effort.
It absolutely will. We'll need physicists, engineers, material scientists, environmental scientists, policymakers, all working together.
So it's a really interdisciplinary challenge.
It is, and one that has the potential to change the world.
So what are the immediate next steps for researchers? What's the focus going to be on?
Well, the short-term focus is likely going to be on material innovation, trying to find and create new materials that can extract energy from the Earth's rotation much more efficiently.
So the search for the perfect material continues.
It does, and there will also be a lot of work on increasing the energy output of individual devices, maybe through design changes or by finding ways to combine multiple units.
So we're still in the early stages, but the potential is definitely there.
Absolutely. It's like we've opened a door to a whole new world of possibilities.
So to sum up this experiment, has shown us something truly remarkable, that it is actually possible to generate electricity from the Earth's rotation and magnetic field, and that overturns centuries of scientific belief.
I know, it's pretty mind-blowing. And while the manganese-zinc ferrite device that they've developed only produces a tiny amount of power right now, it's a proof of concept. It shows us that this isn't just science fiction. It could actually become a reality.
And while there are some huge challenges ahead, scaling up the technology, considering the environmental impact, and addressing the ethical questions that might come up, the potential rewards are huge.
They are indeed.
It feels like we're at the very beginning of something that could be truly transformative.
It's a really exciting time, and that brings us to a final thought for you to consider.
Okay, I'm listening.
What would it mean if we could actually tap into the forces of our planet to provide clean and reliable energy? How would that change the world? And how would it change our relationship with the Earth?
That's a really great question, something for all of us to think about. Thanks for joining us for this deep dive. We'll see you next time.
See you then.